I just wanted to say today, I know a few of you are really new to Python, and that can be like really overwhelming to getting into new tools. So at various points today, I'm very happy to like step away from the activities. The only one I'm actually running is the man and lower phase diagram and meet you guys one-on-one in breakout rooms. So if that's something you're interested in, if you just need a bit more help with the Python, send me a DM on Discord, and I'll either meet you on your own, or if there's two people who are struggling together, we'll do that at the same time. Matt is also going to send around a link to some office hours, which he's going to start up. And that will again give you opportunities to get extra help, particularly once you take what you've learned from this workshop and start applying it to your own research. So yeah, Matt, did you have any other introductions for the day?
No, other than yeah, the office hours, I will basically be posting about that on the Discord page. Like I'll be putting a Google form up for people to sign up to certain slots and stuff. If you want to sign up, I'll be posting the link through the Discord just to keep my email threads a little bit neater, essentially. So keep an eye on the Discord if you do want to kind of follow up on anything in a future week. That's basically it, I think. The two breakout rooms are now open as well. So
Okay, so this morning, the first hour is a session titled Debugging with alphaMELTS. And the point here is that as amazing as Pet Thermo Tools is, and as powerful as it is, you can't do everything there. And in particular, because the next calculation does not inherit the output of the previous calculation after it returns to your notebook or to your control, it's difficult to debug because you can't just sort of play around and take a state and push it this way and that and see what happens. And so I'm going to show you a couple calculations that run into trouble or that do surprising things in Pet Thermo Tools, and then show you how to diagnose and fix those problems using alphaMELTS. And then later today, I'll be back for a session titled something like the 11 biggest problems with melts, where I will walk you through some of the things that the melts insiders know that have somehow never gotten published. And so if you don't come to one of our workshops, you just don't know about these issues. So let me go ahead and get started with alphaMELTS debugging. So the first thing we need to do is make sure that everybody can actually run alphaMELTS. We have some new installers that Paula has built that should make this relatively seamless, we hope. We'll find out in a minute. So if you are using macOS, you should already have Homebrew installed because you needed it to install the new science library in order to do everything yesterday. And so there's just a sequence of 2 commands to type into your terminal. The first one, brew tap magma source / lava -spout, you should only ever have to do once. And then anytime a new version of alphaMELTS comes out, you will need to do the second one, brew install alphaMELTS. So if you are on Mac, go ahead and give it those 2 commands. I also typed them into the Discord because I'm going to hand screen sharing to Paula in a minute, and so you won't see this slide anymore. If you're on Windows, the installer runs through an installation program called Scoop because you don't have Homebrew. And so after installing Scoop, there's a sequence of 2 commands, one of which creates the bucket that, again, you only have to run once. And the second one actually installs alphaMELTS. So let me stop sharing and hand over to Paula, who has a Windows machine running, where she can show you what this sequence of operations is going to look like on Windows.
And yeah, hi, Brad. I saw you had your hand up. Are you? Now you've got both hands up, but no sound.
Yeah, I was just hoping to get more clarification, but I imagine you're about to do so. So please.
Yeah, yeah. But I'm going to be on a different machine that I haven't turned the video on. So, all right. Let me try to share. Okay, I'm just going to share one desktop, hopefully. If I can just. Okay, so I did paste things into Discord. Hopefully those links will work. But if not, you can if you go to your browser and just type scoop.sh. So Homebrew is at brew.sh and Scoop is at scoop.sh. So and then we're just going to follow this quick start. By the way, can people see what I'm?
Yep. Yeah, we
can
see
they hear
it.
me? Because I'm not very close to.
Yes and yes.
Yep.
Okay, good. So we need to open a PowerShell terminal. So if you're on Windows 11 and you actually type in PowerShell, you'll certainly have Windows PowerShell on your computer that comes installed. Now I already have Scoop installed on Windows PowerShell, so I'm actually going to try and use the other one, which is PowerShell 7, which is something you can install. It's the same idea as Windows PowerShell. It's a bit faster apparently, but I haven't actually used it, so I'm just using it as an example. But like I say, everybody should have Windows PowerShell and they should be able to open that. If you're on Windows 10, I have one in front of me, but I can't share the screen on it. If you right-click the start button in the bottom left-hand corner, about halfway down, the options will be Windows PowerShell. Then there may be Windows PowerShell admin just under that, but just do regular Windows PowerShell. That should work. Okay, so here is the PowerShell 7 that I already opened, and I'm just going to copy. We'll see whether this works because like I say, I haven't done it on this before. And if you click copy, and then if you right click, it should paste, and you'll get this warning, but just do about pasting more than one line, but you can just do paste anyway and see what happens. Okay, for me, it's saying that it's already installed, so that's fine. Let me do Scoop update. For everybody else, is it doing something? Yeah, Brad says yes.
Yeah, the first thing it does, I've just done it on my other machine, is it gives you an execution policy change, which I'm guessing you just need to hit yes to, and then it should run exactly what you're seeing here for the update as well.
Yeah, it's actually unlike Homebrew, which does require an admin password one time. This shouldn't require an admin password at all. So it should be good. Okay, so then because I have apparently already got, I'm just going to uninstall alphaMELTS so that you can see what happens when I so you then need to copy in this. It's a good idea to do scoop bucket add extras. So it's going to tell me that I've already done that, but okay. That's just got some extra utilities and things that you may turn out to be useful. And then we're going to do scoop bucket add lava bucket, and you can copy this from the PowerPoint or from the Discord now. Magma source, or one word, lava bucket. And I don't play Minecraft, but my kids do, and apparently they have lava buckets and lava scoops, lava spouts. So um, uh, Paul used to have Minecraft on his machine. I remember, like back in the
I
days.
also have kids.
Yeah,
Yeah, so
exactly.
a couple of people are saying they've got issues. Yeah, if this is the first time running PowerShell on Windows, you might have to run scoop install git first before you do scoop bucket add extras. It will take a couple of minutes, but then you should be able to go through the steps Paula has just shown.
Yeah, I mean, I certainly did that in the past, and it's obviously a little diff. Yeah, so if it tells you to do something, just follow blindly. That's what I did when I originally installed this, and I can yeah, so just do whatever it suggests, um and yeah, because you'll need Git for the lava bucket to work. So okay, and then so yeah, let me know when you're okay, or if anyone's not ready to go further or having more issues. Just let you know. So then we're just going to do scoop install alphaMELTS, all lowercase. It shouldn't matter, but it's and you should now be able to go. Let's go somewhere. I don't. What I don't have is the. Let me go. Yeah, so I'm just switching to the other one, other window, the Windows PowerShell, because I know that's in my home space. But like now, wherever I am, I should be able to do run alphaMELTS. Calls it out. Don't see, but hang on 1 second. Okay, for some reason that's not working. Run alphaMELTS. H. Let's see. No. Okay. It might. Okay, you're gonna have to give me a minute to check what's happening here. Okay. On Mac, oh, here we go. Okay, so can people on who have run the homebrew version verify that they can type run alphamelt run-alphamelts.com command -h and it brings up yeah. Okay, so give me a couple of minutes to sort out what's going on here, because it was working absolutely fine, and of course that's what always happens with workshops. I'm going to switch my Zoom to the I'm going to stop screen sharing for a minute so that Paul can start talking, and I will chip in as soon as I have. It might be as simple as like need to restart PowerShell, but just allow me to take a couple of minutes while Paul starts explaining. Yeah.
In Windows, it worked for Giannis.
Oh, okay, good. What have other people found?
Any Windows users not able to successfully run alphamelts.command-h and get the help info? At least one not working.
Okay, I'll like I say, I'll stop screen sharing for a minute. Where are we?
Okay, when you have a fix, come back.
Yeah.
And
just
I will start sharing.
yeah, just 1 second, Paul. So this is what it should look like if it's working. This is obviously the Mac version.
Yeah.
Okay. And now I'll have to work out how to stop sharing again. Okay.
Okay. Yeah, so if, as Paula just showed, if you have installed alphaMELTS such that it is in your path, then when you open a shell, a terminal on Mac or PowerShell on Windows, and you type the command run -alphamelts.command, the hyphen is important because the command to run the old alphaMELTS 1.9 was run _alphamelts.command. And if you just say -h, which means print the help, it doesn't actually run the program. It just proves to you that it knows how to find it, that you are running the current version, and it shows you the full list of things that you can type on the command line to set various options for alphaMELTS. Okay. But just hold on to that for a minute now that you're installed, because the other things you will need to do the exercises
Paul.
this morning. Oh, go ahead, Paula.
Yeah, okay, so it works actually as long as you only put either run alphaMELTS or run alphamelts.exe and don't add the .command.
Okay. So on Mac, you definitely want to type run alphamelts.command. On Windows, just run -alphamelts without the .command.
So on Mac, you can do either .command or not now.
Oh, okay.
In the past, you had to do .command. Now it's that bit's optional. And in fact, it will actually be going to optional between .pl and .command in the next version. We're just going to stop thinking about the extension altogether.
Okay.
And just use it. Anyway, I will stop into.
Okay, so in addition to having the software installed and able to speak to you by giving you its help info, you also want to get this new Jupyter notebook and 3 directories of alphaMELTS examples. They are posted as a zip file and as a Dropbox link in the Day 2 Ask for Help channel. So please download those files. And while you're doing that, let me just introduce what you think you should know about fractionating a basalt so that we will recognize the anomaly that's going to happen when we try fractionating a particular basalt, first in PET thermotools and then in alphaMELTS. So obviously fractionating magmas, primitive magmas, is one of the main things that people use melts for. Usually we do this calculation at low pressure. That's where most fractionation happens in the earth because the lithosphere is cold. And so usually you do this in rhyolite melts and not in P-melts. Most often the calculation that we run, the most generic sort of differentiation process that we imagine, is isobaric cooling accompanied by perfect fractional crystallization. So you hold the pressure constant, you compute an equilibrium. If there are any solids, you remove them from the system, and then you cool the residual liquid by a little bit and do it again and keep cycling. But that's not by any means the only calculation we can run. We can do equilibrium crystallization where you don't fractionate. We can fractionate some, but not all of the phases in alphaMELTS 2, which is a nice trick. We can ramp the pressure while we are also ramping the temperature if we imagine that we're looking at some sort of polybaric fractionation process. Have a number of options we can implement. We most often will run a forward model where we start with a primitive melt and we cool it down, but it's not the only calculation you can do. Certainly in alphaMELTS, you can do a reverse fractionation calculation where you go slightly below the liquidus, see what the liquidus phase is, and then assimilate some of it to make a more primitive bulk composition. And then you go up temperature to the new liquidus and do it again. And so to some extent, you can reverse the process. we normally, most generically, will do our fractionation as a closed system, except for buffering the FO2, which means the system is open to exchange of oxygen with the environment. But we can also do assimilation calculations. We can do recharge assimilation calculations. We can script together a number of complicated processes. For AFC, and especially for our AFC, the magma chamber simulator is set up to automate all of the bookkeeping involved in doing that calculation, and that may be the best way to do it. So let me show this as a PowerPoint slide. Here, just to illustrate kind of what we expect out of a fractional crystallization calculation, I have a plot of weight percent alumina versus weight percent MgO, and the dots are all of the mid-ocean ridge basalt glasses that were in the PET-DB as of about 20 years ago or something when I made this slide, grouped by ocean, okay? And you can see that there are some systematic trends here, which we associate with the effects of low pressure fractional crystallization. Specifically, what we imagine is going on here is that there is some primary liquid that comes out of the mantle and ascends into the oceanic crust. Nobody's ever seen it, but it's probably over there somewhere, around, depending on the mantle potential temperature, 10, 12, 13% MgO. When it starts cooling, the first thing that happens is it fractionates, saturates with, and begins to fractionate olivine. Fractionating olivine makes a dunite, and the residual liquid, as you remove dunite, moves towards lower MgO and higher alumina for a while, until it gets high enough in alumina to saturate with a second phase, which at low pressure in relatively dry tholeiitic magmas on Earth will be plagioclase. And we will start fractionating plagioclase plus olivine, which is troctolite. It's a very high alumina rock, and will drive the residual liquid steeply downwards in this plot for a little while. Only for a little while, because we then typically saturate with our third phase, which is clinopyroxene, and we start fractionating gabbro, clinopyroxene plus plagioclase plus olivine. And we typically do that for quite a long time before saturating with any other phases. And gabbro fractionation both explains the main composition of the oceanic lower crust and the main trend of variation that we see amongst glasses that are erupted at mid-ocean ridges, right? Typically, once we add a phase to the fractionating assemblage, it stays in the fractionating assemblage, possibly until it's replaced by some other phase. Okay, so somewhere down here, we might pass through a paratectic where olivine goes out and low calcium clinopyroxene comes in, or we might go far enough to saturate with an oxide phase, right? So this is just what we expect to happen. And when we run a calculation, we'd like to see that happen, but I'm going to run a calculation where it's not quite what happens. Okay.
You're going to find Dada.
Hello, Augie Ryan Davis.
Oh. Sorry.
No worries. So what I would like you to do is get PET thermo tools going again and open up the Activity 6 Crystallization with Glitch notebook. Okay, so I'm going to try to stop PowerPoint here and go to the directory where I have the Activity 6 Crystallization with Glitch notebook, and I'm going to start up Jupyter. You do this exactly the way you did this yesterday, however you got your Python working. And I'm going to open up Crystallization with Glitch. And here I am in a Jupyter notebook to run PET thermo tools, same as yesterday. Brad is asking for a link to the GitHub. Would somebody please post that link? Okay, so remember that when we go into Pet Thermo Tools, we need to import a bunch of stuff, including Pet Thermo Tools as PTT, and it's good practice to always have your Jupyter Notebook tell you what version you are running, so you can make sure it's the current one. Okay, 0.3.15, or as Matt and Penny would say, not 0.3.15 is the version I have installed. Usually by default, when you display a data frame in Pandas, it only shows you the first 5 lines and the last 5 lines. If you set display max rows to none, it will show you all of the lines of your output. So if you need to do debugging that involves looking, in this case, at the 8th line of the output, it will be there. Okay. Remember that this suppression of output prevents you from having to see the giant spew of all of the kind of debugging level output from alphaMELTS. So Divya, activity 6 is in the new files that were posted on the Discord this morning. There is no activity 5. I just guessed without looking that the next one I needed was 6. So you need to get activity 6 from the link. There we go. So I'm going to go ahead and suppress output. You run this cell twice. Okay, and then this notebook is documented a little bit. It says what we're doing here and what you expect to see. It says one disadvantage of Pet Thermo Tools is that a run that crashes before the stop condition will not return any data. For example, we're going to try running this calculation with the end temperature set to 600 degrees C, okay, which is too low. Melts will crash before it gets all the way down to 600 degrees C. And we're going to use this particular glass composition, Kilo Moana 2004 Cruise 17 Rock Core 12, which was collected on a cruise in the Lao Basin and published in this paper by Antoine Bezos. Okay, and then this is just the Pet Thermo Tools isobaric crystallization function set up to use Rhyolite Melts 1.2. Okay, to find the liquidus, and then at 250 bars to simply cool down at 1 degree steps at FMQ -1, fractionating solids, and trying to get all the way to 600 degrees. Okay, and so I will run that, and I can see from the star that it's running. If I looked at my terminal, I can see it spewing various information as it goes, but it's not displayed here in the Jupyter Notebook. Okay, and it finished. And if I now ask it to show me the output is empty. There's nothing there. So I know it ran a bunch of calculations, but it did not return anything, okay? And that's because the last calculation was a fail. So one thing we can do is say, okay, let's just guess that if we stopped at 1,000 degrees, life would be better. So if I run that calculation again, telling it to terminate at 1,000 degrees, it runs for a bit, a few seconds, finishes. And now if I ask to see the output frame, there's a whole bunch of stuff, right? And in particular, it started at 1190, it went in 1 degree steps, it got all the way down to 1,000 at step 191, and it returned all the data. Okay, so that's good. We have a calculation. So one reason that you might want to have alphaMELTS available, even if Pet Thermo Tools becomes your primary modeling tool, is how did I know to stop at 1,000? Well, I just pulled that number out of the air. Whereas if I ran an alphaMELTS, I would see as it's running the temperature at which it fails. And I would know that that's as far as I should go. And also alphaMELTS stores its output as it goes so that even if you crash, you still get all your information and you have a complete log of the successful calculations. Okay. So that said, one reason to use alphaMELTS is it's easier to see what's going on and easier to debug. Let's look at the crystallization sequence that we got when we successfully ran from the liquidus at 1191 down to 1,000 degrees. Okay, so calculation 0, you can say isobaric crystallization, that's the output data frame. And let's look at the array in that data frame called phase list. Okay, so at steps 0, 1, and 2, the assemblage is liquid plus plagioclase. So this is not a primary composition that came out of the mantle. This is a composition that had already been fractionating before it was erupted. And it happens that it's very close to the plagioclase olivine cotectic. It may well be that in fact it is on the plagioclase olivine cotectic at the conditions where this magma was fractionating, but I don't know those conditions exactly. I picked a pressure 250 bars out of the air, okay? And I picked a water content based on the analysis of the rock, but there's uncertainty on that. And I picked an FO2. I could easily vary the pressure of the water content in the FO2 to get this glass to be exactly co-saturated, because it only went 3 degrees worth of plagioclase crystallization before it started also crystallizing olivine. Anyway, this is normal behavior. So it crystallizes plagioclase for 3 degrees, then plagioclase plus olivine for 6 degrees. And then at step 9, it switches to plagioclase plus clinopyroxene. Now, it is a petrologically reasonable thing for clinopyroxene to replace olivine on the liquid line of descent. That's what happens when you get to the paratectic and you start fractionating on Earth, typically OPX, and on Mars, typically pigeonite, right? And sometimes on Earth, pigeonite. But that's not what happened here. We're way up at too high a temperature and too primitive a lava for that to happen. And we can see that it's wrong because if we go 6 degrees further, olivine comes back in. And that's weird. That's weird to get on to the plagioclase plus olivine cotectic, to have CPX come in and push olivine off, and then to have olivine come back, right? And once we get past that weird bump here, then everything is kind of normal. We crystallize a gabbro assemblage for like 50 degrees, and then we add an oxide phase, in this case magnetite. It shows up as spinel. And then we crystallize that for a while. And then we get to the actual paratectic where olivine goes out and pigeonite comes in, okay? So the issue that I'm raising here is, what's this? What's this phenomenon just 12 degrees or 9 degrees below the liquidus where CPX came in and olivine went out, okay? So one thing we can do to investigate that is we can output from our PET Thermotools output data frame the table called mass G, which looks like this. For each calculation we ran, it shows us the masses of each of the phases in the instantaneous calculation, and then the cumulative masses, because it's a fractional crystallization calculation, and sometimes you want that. So we see again, the first calculation is liquid plus plagioclase, just a little bit of plagioclase because we're right up near the liquidus, okay? That plagioclase gets fractionated, and in the next step, we have liquid plus 1/3 of a gram of plagioclase. And you can see the total amount of plagioclase crystallized is the sum of those first two numbers. And then at the third step, we crystallize roughly the same amount of plagioclase again. Then olivine joins the assemblage, and we crystallize, you can see, about 0.6 grams of plagioclase and 1/4 of a gram of olivine per step. And we come down here to step 9, and we crystallize 2.7 grams of CPX all at once, and we stop crystallizing olivine. And in 1 degree steps, that's anomalous. That's a lot of CPX to come out all at once. And in fact, you can see by looking at the subsequent steps that we really only should be crystallizing about 0.7 grams of CPX per step. Okay, so I recognize that something funny happened here. I recognize that when CPX came in, it came in too fast. And what's going on here is, well, first of all, I can show that this is an artifact by repeating the calculation, not in 1 degree steps, but in 0.1 degree steps. Okay, so we should get 1/10 as much crystallization per step. Okay, and for this purpose, I stopped the calculation at 1175, so we don't generate thousands of calculations, okay, just again a couple hundred. So I'm repeating the calculation from the liquidus, but going in 1/10 of a degree steps, okay? We'll run that. It will execute for a little while. It has a clean stop, so it returns data. This crystallization is called isobaric crystallization small step. And when we look at its mass table, okay, we see a much smaller amount of plagioclase per step, in fact, 1/10 as much, for 30 steps instead of 3, and then olivine for 60 steps instead of 6. And so if you scroll down instead of to step 9, you scroll down to step 8 to step 80, you can see we're still getting 2 grams of CPX, even for a 1/10 of a degree step. Okay. And again, that's weird. Okay. So what's happening here is the model is trying to follow the plagioclase olivine augite cotectic. That's what it wants to do. But in multi-component space, that cotectic is a curved line. The phase proportions and compositions need to change as you follow that cotectic. Okay. And when you crystallize a whole bunch of CPX all at once, it pushes you off the cotectic and away from olivine crystallization, and you lose olivine from the assemblage, and it takes another 6 degrees of plagioclase plus CPX crystallization to push the liquid back onto the cotectic. And that's really not what it should be doing. The reason it's doing that turns out to be a shortcoming in the routine that detects phase saturation, that decides, oh, I'm saturated with clinopyroxene, I'm going to add it to the assemblage and consider it in subsequent calculations, right? It needs to be somewhat oversaturated in CPX in this case before it recognizes that it should be adding CPX, and it's going about 3 degrees too far past where CPX should come in before it comes in, and by that time it's very oversaturated with CPX, and so it dumps a whole bunch all at once, and as a result it goes in a straight tangent line away from that phase assemblage, and it pushes itself off the cotectic. Okay, so you may not care about this little wiggle, but maybe you do. So what can you do about it? Okay, in PET thermotools at the current time, not much. Okay, so reason 2 to consider having alphaMELTS around as an accessory or as your main modeling tool, okay, is that we can work from the menu to manipulate the system and work around problems like this. So let's go do that. Okay, so I'm going to go to terminal. Actually, first I'm going to go back to Zoom and see the chat. Oh, Lauren needs to see the Discord link one more time because quitting Zoom makes
I can do that.
Okay, makes your chat history go away. Okay, so I currently have 3 terminal windows open. So on Mac OS, we need the terminal program. On Windows, you need a PowerShell, and we're going to talk to the terminal or to the PowerShell. And we're going to need a few shell commands to figure out what's going on here. Okay. One super useful one is pwd, print working directory, okay, which is telling me which directory I'm in, okay, and cd ... means change directory, go up 1 level. cd ... means change directory, go up 1 level. Okay, and now on Mac, the command to see what's in a directory is ls. On Windows, it's dir. Okay. And you can see that in this folder of a bunch of workshop activities, I have the activity RC12 frac, okay, which is one of the ones that was in the download package that Paula posted in the Discord this morning. So to continue, you're going to need RC12 frac and RC12 frac B. Okay. And so if I go into RC12 frac, CD to change directory, and then I look at what's in there, there are two versions of the exercise, the one that runs in alphaMELTS 2. And if you ever want to try learning to use EasyMelts, which is another front end that is available, there is an EasyMelts version of this exercise, but we're going to use the alphaMELTS one. You may note as you watch me type that I'm using tab completion. In this directory, there's only two files. One starts with an A, one starts with an E. So if I type A tab, the shell is smart enough to figure out what I want. This is super useful because file names can be really long and really easy to mistype, and tab completion just saves you all of that trouble. Okay.
One thing of caution is that tab completion works slightly differently on Windows, so you probably have to type a little bit more. It sometimes means that you have to type a bit more of the name before it gets. If you just do tab, it will take the first alphabetically rather than whereas on Mac it will only complete as much as it's certain of.
Mm-hmm.
It doesn't make any difference in this case because there's only two files that begin with different letters, but when you have like a lot of slightly similarly named things, then it can make a difference.
Excellent.
Anyway,
point.
yeah.
Thank you.
But PowerShell is much more similar to the Mac terminal than the
Windows command line.
Yeah, than the Windows command.exe. So using PowerShell makes it a little bit more consistent experience.
Cool. Okay, so in the alphaMELTS 2 subdirectory of RC12 frac, there's a bunch of files. Okay, one of them is a .melts file, which is the standard way that melts calculations are set up in alphaMELTS. Let me just show you what it looks like. You don't have to make a file because we're giving you one, and you can take any existing melts file and edit it to make a new one. But if I use the command more, which will just type the contents of a text file, and then capital K, and again, you can see there's only one file here that starts with capital K, so I can just say tab, and it fills it in. Okay. There's the structure of this file is keyword value with a colon. So the title is KM0417 Rockcore 12. We set up a bunch of initial composition lines that give us the composition in grams of oxides. You may recognize that's the same composition that we gave to Pet Thermo Tools a moment ago. The initial pressure and final pressure are set up as 250 bars because this is an isobaric crystallization calculation. The initial temperature is set to a value near the liquidus, so we don't have to do find liquidus. The final temperature is set to 600, which remember crashed Pet Thermo Tools. The temperature increment is -1 degree. The sign matters. We want to go down. The FO2 path is 1 log unit below FMQ, and we're going to be fractionating solids. Also, we're going to output files in both the alphaMELTS and MELTS GUI formats. So to run alphaMELTS, also in this directory, very important, there's a file called readme.txt, which has step-by-step instructions that show you what we're going to do. Okay, so I'm going to use more. You can use any text editor you want to display the contents of readme.txt. Okay, which explains what we're doing. We're doing isobaric fractional crystallization of a back arc basalt using alphaMELTS 2. There is water and CO2 in this calculation, so we need to use Rhyolite Melts 1.2. Okay, and then here is the exact sequence of commands that we're going to start typing in to alphaMELTS to reproduce the calculation that we just did in Pet Thermo Tools. Okay, so I have this other window here so that I can have the README displayed on one side of my screen and run the calculation on the other side. So I'm going to say PWD to see where I am. I'm in a different folder, so I'm going to move to the right one. I have to go up 2 levels. I have to go into RC12 frac. I have to go into the alphaMELTS 2 directory. Now I'm in the same directory as the files are in. Okay, so This is an important thing about operating at the command line in any shell, whether it be PowerShell or command line or terminal on macOS. At any point, there is a working directory. The shell thinks that everything you type will start with the path name of that directory that is the working directory, and that will control, in some cases, which input files you can see, and it will control where your output goes. And so it's very handy, it's essential really, to know what directory is your working directory, so that you know where your files are coming from and you know where your files are going. Okay. So in this directory, I can now start alphaMELTS. So I'm going to type run -alphaMELTS on Mac .command. On Windows, you don't need the .command. And then remember that when we said -h for help, it showed us all of the options that we can put on the command line. There's a bunch of them, okay? But right now, the only one that I want is -p, which is how you specify the output path, okay? And this is an important aspect of your work habits when you're using alphaMELTS or any number of software packages, but alphaMELTS in particular. Every time it runs, it creates a whole bunch of output files with the same file names. And if you don't control where you're putting your output, you're always going to be overwriting previous files that you created. So by using the p command to direct the output to a new directory, right, I can make sure that I'm putting my output somewhere where it's not going to overwrite previous information and where I can find it again. Okay, so let's just name this output, for example, output January 13th, 2026, so that I know that it's this particular calculation that I'm doing today. Okay. When I run that command, instead of giving me the help info, okay, it starts the program. It sees that it's version 2.03.01, and it's happy with that. And it returns the command alphaMELTS calc mode not set. In other words, we haven't told it which version of the model we want, okay? And the following sequence of questions, the answers are somewhat counterintuitive because of the way the questions are posed. So read them carefully the first time. After this, you'll get into the habit. It says the default calculation mode is alphaMELTS 1.0. Change this. Okay, so if you want alphaMELTS 1.0, you say no. If you want some other model, you say yes, I want to change it. Okay, so give it a Y for yes. And then it says, do you want alphaMELTS 1.1? Now we don't, we want alphaMELTS 1.2. So the answer here is no, I don't want alphaMELTS 1.1. Okay, so the first question, to change away from 1.0, I said yes. Then to reject 1.1, I said no. And then it asks, do you want 1.2? And we do want 1.2, so we'll say yes. Okay, so Y and Y. Yes, I want to change from 1.0. No, I don't want 1.1. Yes, I want 1.2. And then you get to the main alphaMELTS menu. Okay, has some info about what program you're running. And then it has this menu of things that you can do. The first thing you do, unsurprisingly, is almost always option 1, which is to read an input file. Okay, so we say option 1, and now we need to tell it the name of the input file. Now, Paula went to a whole bunch of trouble to get tab completion working here inside alphaMELTS. So we can just type capital K, because there's only one file in this directory that starts with K, and tab. And I don't have to go find the whole name of that file, kmo417rc12frac.melts. I can just type ktab. Of course, I could also scroll back because I listed the contents of the directory just before I started, and I could copy that. You can also drag and drop it. You have a bunch of choices. Okay, so we tell it the name of the input file, we hit return, and if it works, it just tells you that it worked. If there's something wrong with your input file or it can't find it, it will tell you that. Okay? And now you can use option 2 to change the initial pressure and temperature. We don't need to, okay? You can use option 3 to do a single calculation to verify that your starting condition is where you want. You can manipulate a bunch of things from the menu, but because our input file is set up to do exactly the calculation we want to do, we can just go straight to option 4 to execute, which means start down the path that has been defined. The path that is defined is isobaric cooling in 1 degree steps until you get to 600 degrees. So we can say execute. Okay, before it goes, it's going to ask a couple of questions. Okay, and we see something here that has not been explained yet. Okay, when you start a MELTS calculation, you need an initial guess. You have to feed it a potentially correct solution that satisfies the constraints so that it can improve on that guess. Okay, and in most versions of MELTS, the only initial guess that is available is that the system is above the liquidus and consists of 100% liquid with the same composition as the bulk composition. Okay, but in alphaMELTS, we have a customized norm calculation. It is not the CIPW norm, it is a different norm that will take the oxide weight percents that you give it, or grams that you give it, and map them into a solid assemblage of MELTS minerals that satisfies the bulk composition constraint. That is available to us here, option 0. Option 1 is superliquidus at the current temperature. Option 2 is do a find liquidus operation before it starts fractionating. And option 3 is do a find wet liquidus operation. I will talk later about the difference between find liquidus and find wet liquidus. Suffice it to say that if you're water saturated, find liquidus won't work. So we're going to say option 1 because we've already set it to the liquidus temperature, so we don't need to search. Okay. And then before it goes, because once you say go, if you don't tell it to stop, it's going to go for a long time. We have some choices. We can tell it 0, meaning just go until you hit a stop criterion, like the minimum temperature or a crash. Okay. Or we can put in a positive number, which in this case means do that many steps before you stop. Or we can put in a negative number, okay, which is code for if you hit a bad calculation, go ahead and step over it and keep going that number of times. So -4 would mean it's okay if you hit a bad calculation, try again, try again, try again, then give up, okay? So we know, because we ran this in Pet Thermo Tools, this same calculation, that the funny business happened at step 8, okay, and was resolved 6 degrees later by step 14. So I'm just going to tell it to do 20 steps, okay? I could let it run all the way down. It will crash before it gets to 600 degrees, but all the output will be saved, but I don't need to demonstrate that. I'm just going to do the 20 steps, and I'll say go, okay? And it goes, and it does 20 steps in the blink of an eye. And now you can scroll back and you can see what happened here in the terminal, okay? And once you get used to reading these things, you can read them pretty fast. So the first step at 1191, okay, was all liquid. Okay, I better pause and see what's going on in the chat, which is just Discord links, okay. So the first calculation at 1191 was all liquid, 100.6 grams of it, okay. And then we brought it down to 1190, okay. And we see that plagioclase has joined the assemblage. So now there's 100.2 grams of liquid and 0.36 grams of plagioclase, okay. We get to the next step, 1189, okay, and it fractionated that first batch of plagioclase and made some new plagioclase, okay. By the way, it's also giving you the molar formula of the plagioclase, so you can see that the plagioclase is AN79, albite 21, a very primitive plagioclase, which is a sensible thing to come out of a primitive mid-ocean ridge basalt. okay? And we keep going, and at 1188, we see that olivine has joined the assemblage. What olivine? Forced to write 82 olivine. Oops, I did not mean to do that. We were at 1188, sorry. Forced to write 82 olivine. Okay, and then one more degree, olivine plus plagioclase, olivine plus plagioclase, olivine plus plagioclase, and then here at 1184, olivine plus plagioclase, olivine plus plagioclase. Okay, at 1182, the glitch happens. The glitch is 2.5 grams of clinopyroxene all at once and no olivine. And then we see no olivine, no olivine, no olivine, no olivine, no olivine. We got to get all the way down to 1176 before olivine comes back. Okay. Yeah, I'm going to finish at about 10 past 9, and then we'll take our break and move on to the next step. I need a little bit of extra time compared to the original schedule. Okay, so we hit the same issue that we hit in Pet Thermo Tools here in alphaMELTS, that we got too much CPX when CPX came in. But here in alphaMELTS, okay, we can do something about it. So I'm going to type X. I'm going to try to type X to quit. And I'm going to move over to the RC12 frac B directory, which is the same calculation except with the extra trick described in the README. Okay, so I'm going to go up 2 levels. I'm going to go into RC12 frac B. Okay, this directory, which should also be in the files that you downloaded this morning.
So for the ones that you downloaded, everything is just in RC frac and RC frac B. So you only have to go up 1 level for them.
Okay.
I didn't put the AZMelt stuff in, files in, because I thought that would just add even more confusion. So so they only have to go cd ... and not cd ... /...
Good. You can always list and pwd to see where you are if you're navigating, so you don't get lost. Okay, so I had to go up 2 directories because of my directory structure to get to this directory so I could find RC12 frac B, and then I stepped into it, and then you don't have to do the cd alphaMELTS 2. You'll already be in the RC12 frac B directory where you have the input file, and most importantly, the README. Right. And so when we look at that README, okay, it's going to narrate here the sequence of steps that we're going to do differently to avoid this particular problem. Okay, and so I'm going to move my other window into that directory also. And then, once again, I'm going to run alphamelts.command. I'm going to use -p and name my output directory, whatever I want, just so I know that it's unique and I'm not going to erase anything I did before. And then remember, to get RILIMELTS 1.2, we say yes, no, yes. And here we are at the menu. We say option 1, we want to read in our input file. I'm going to type K tab, and it's going to fill in the name of that input file. Return, and it says it read it, and so I'm all ready to go. Okay. Now, at 1182 degrees in the previous calculation, I got about 3 degrees worth of CPX crystallization all at once. Okay, so what I'm going to do here is just go down to 1186, which is the last step before CPX is supposed to come in. Okay, so I'm going to run option 4, superliquidus initial guess, and I'm just going to do 6 steps. 1191, 1190, 1189, 1188, 1187, 1186. And it just does the 6 steps and it returns to the menu. Okay, and now here's the power of alphaMELTS. It knows where it is, it remembers the current state, it's still there in memory. I can manipulate it and then start running again. Okay, so when I stopped at 1186, I'm still fractionating just olivine and plagioclase. Okay, so here's the trick that we have figured out to get around this particular problem. Okay, so this is step 5 in the instructions. We're going to use menu option 2, which is called twiddle starting or continuation parameters. And we see the parameters that we can change. The initial temperature, the final temperature, the temperature increment, the initial pressure, the final pressure, the pressure increment. And I'm going to change the initial temperature, number 1, and I'm just going to jump down to 1182 degrees C. Okay, and then throughout alphaMELTS 2, anytime you need to step out of a submenu, you type X. So I'm back to the main menu, and now the temperature is 1182. And now here's the trick. Option number 3 in the menu is labeled single batch calculation. So it just does one calculation and returns to the menu, and that calculation is always batch. It will not do any fractionation. And that means that it won't affect the bulk composition of the system. And so it's a safe trial balloon. It will not mess up the sequence of things I'm trying to do to follow my fractional crystallization trajectory. So I say option 3, it executes and it puts a bunch of CPX in. Okay. Now CPX is in the assemblage. I have overcome the nucleation barrier, the numerical nucleation barrier that was interfering with getting the right calculation path. Okay. And so I can now use option 2 again. Okay. Now we're at step 7 of the instructions here. And I can bring the temperature back up to 1185, which should be the next step after 1186 in a fractional crystallization calculation with 1 degree steps. Okay. So I change to 1185. I exit this sum menu. Okay. I can do a single calculation now, a batch calculation with option 3, just to check that it worked. And I can see that I found a state now at 1185 that has the right amount of CPX. 0.6 grams per step is about what we expect to get for 1 degree calculation. Okay. So I drove the system around a nucleation barrier. I stopped the fractional crystallization calculation. I went down far enough to force it to crystallize CPX. I brought it back up to where it should have been crystallizing CPX. And now CPX is in the assemblage. And so the glitch in the phase saturation algorithm is not going to cause me trouble anymore. I can now just go ahead and say option 4 to let it execute again as many steps as I want. And now, because I have already said option 4 once, and I have 6 calculations in the array of results stored, I get a new question. Do I want to record these steps from scratch or append to the previous? And what I want to do is glue the rest of the run onto the previous steps I did. So I will say 0 for append to previous. Okay. And I could say just go forever and would spew a whole bunch of output, but I just want to show you, say, the next 10 steps. So I can scroll back and look at what happened. And what I see is it just went on about its business with olivine plus CPX plus plag, with olivine at every step. We never forced olivine off the crystallizing assemblage. We have smoothed out the glitch and gotten a smooth progression from plagioclase to troctolite to gabbro-fractionation without any wiggles. Okay, so the main point of that exercise was I used alphaMELTS to do that because I can do these manipulations. I can do some calculations. I can return to the menu. I can change the state. I can test things. I can dance around in ways that currently with the packaged pet thermotools functions like ptt.isobaric crystallization does the whole calculation for you if it works. If it doesn't work, it's hard to know why it didn't work, and it's hard to fix it. Okay, so I will be back later with some more issues and fixes that apply to all versions of melts, some of which can be fixed in any version of melts, some of which are most easily addressed using alphaMELTS. But that's my time this morning, so I'm going to stop there.